So tomorrow in the video, we'll discuss combustion analysis. We'll go through the math and everything like that. I'll try to keep it as short as I can. No guarantees, though, because I like to try to explain as much as I can in the videos. So we'll see. Anyway, before we begin, next week, since you ain't going to be here, the lab that I had planned, what I will do is I will kind of run it myself, and then I'll do snippets of the process, of the reaction happening, and I'll indicate to you what data points I want you to write down on the printout, okay? And since you're here, I'll just give you the printout now. That way you don't have to print it out at home. It's unfortunate because this is actually a really cool lab. And the more people that do it, the more money that I get for my retirement fund. So I described to you what this lab involves. This lab involves predicting how much product would be produced, or predicting how much reactant was used. And the end result is real silver. We take a solution that contains silver and actually cause a reaction to where the silver then goes onto a copper wire. So you take that silver outside of the solution and you get silver. See? And this is over a few years worth, okay? I think I have calculated this to be, roughly calculated this to be, maybe $1.88. Not very much, okay? And I used to have a sticker on here that said Mr. Dorford Retirement Fund, because I just have all of my students just give me all their silver and I put it in here. First of all, I mean, really can't dispose of silver down the drain, so I guess I keep it, but it's fun. But yeah, it's a really good lab. Just thinks that I'm not going to be able to do it together. But anyway, I'll be conducting the lab. I'm not going to have the camera on it the entire time. It is a 2-day lab, only the fact that you have to let it dry. But I'll kind of pause the video and then I'll restart the video whenever something's happening. So I'll walk you through what you need to put in your packets, and then we'll kind of go from there, okay? New territory in that regard. Anyway, today's lesson, we are talking about finding empirical formulas, okay? Not too long ago, we talked about the different types of formulas. We've got empirical formulas and molecular formulas. Empirical formulas are the formulas where the subscripts are in their lowest whole number ratio, essentially, okay? They can no longer be divisible to make them smaller. They're in its simplest form, whereas molecular formulas indicate the exact number of atoms of each element in a compound. And so what we're going to be doing today is we're going to be taking concepts like the mole and molar mass to help us calculate the empirical formulas of substances. So you have that flow chart, okay? There's really only 3 steps. And there's only a couple of calculating steps, okay? So let's look at this flow chart first, okay? After we've gone through this, we're going to be taking a look at how we can take empirical formulas and calculate the molecular formulas. So a couple different things today. Anyway, on the flow chart, look at this first box on the left. Before we do anything, look at the arrows. Are the arrows going both directions or in one direction? Like your favorite band? Yeah? So you can only go one way. So a lot of the setups are going to be identical. Okay? Very first box on the left says mass percent of elements. And what that means is oftentimes we're going to be given formulas like scenarios that they're going to give us the percent makeup of a substance. So this substance has 14% carbon. This substance has 64% hydrogen. Stuff like that, okay? Or it just might even give us straight into the second box. the mass of each one. But if we get the percentages, we get to make an assumption. Can anybody tell me what that assumption is? Yeah, we're going to assume we have a 100-gram sample. Because when we talk percentages, when you add percentages up, what should the entire percentage sum be? 100. And so we can assume that we have 100 grams of our sample when we're given the percentages of each. So that 14% that I said with carbon, how many grams of carbon are we going to say we have? 14. The 64% of hydrogen is going to have how many grams? 64. Okay. So once we get to the grams of each element, we have to determine the number of moles of each element. And how do we go from grams to moles? We've seen it before. Molar mass. Okay? And then I'll talk to you about calculating the mole ratio when we get there. Okay? Let's look at a practice problem here. The compound para-aminobenzoic acid. That was a mic issue, people. Nothing to see here. You may have seen it listed as PABA if you use sunscreen, which I hope you do. It says PABA-free oftentimes. It's composed of carbon with 61.31%, hydrogen 5.14%, nitrogen 10.21%, and oxygen of 23.33%. We are asked to find the empirical formula of PABA. Okay. So first off, what is the information given to us as? Percent. Okay? So we have percentages. If we added those up, most likely it'll add up to 100%. So we've got percentages. What do we assume? 100-gram sample. Therefore, these percentages will all translate to grams. Get 61.31% carbon, 61.31 grams. Okay. So according to your flow chart, we are at the grams box right now. We need to get to the moles box for each element. So we take the mass of each element that we just determined or assumed, and then multiply by the molar mass of that specific element. And where can we find this information? Where can we find the molar mass of each individual element? The periodic table. It's listed. It's the atomic weight listed there on each element. And so in order to go from mass to moles, we must make sure that moles is on top. And so we go ahead and solve for each one. Now we're at the third step. Okay? We each have moles. What is the last step that we have to do according to your flow chart? Calculate the mole ratio. Let me have a guess as to how we do that. I'm not expecting you to know it, but I'm just trying to see if you are thinking about it. Here's how. After we've calculated the moles for each element, we identify the smallest mole value. Okay? So out of all four of these moles that we calculated, who has the smallest number of moles? Nitrogen. And so what we do is we take that value and divide all of the mole values by that smallest value. So when you take carbon's moles and divide it by nitrogen's moles, you get a value of 7.005. Okay. Now, never mind this number here. Why is 7.005 not an acceptable number when we're trying to figure out formulas? Can you have decimals or fractions of atoms in a molecule or compound? No, you have to have whole numbers, right? And so we can round. Now, there's going to be a question that we're going to encounter here today that we're going to find out that we can't simply round. I'm going to talk to you why. A lot of times we get these fractional value or decimal values from what we call experimental error. Okay, I'll discuss that here in a little bit. So carbon, we round to 7. Hydrogen, we round up to 7 as well. When you divide nitrogen by itself, you're going to get 1. And with oxygen, you're going to get a rounded number of 2. So what do you think these whole numbers that we just calculated, what do you think they are? What do you think they represent? The subscripts. Yes. So the whole numbers that you've determined now become the subscripts on their respective element. So Pava has the empirical formula of C7H7NO2. So now let's do some other examples, okay? In your slides here under the sample exercise. There we go. Let me get my pointer here. Okay, so I'm going to walk through this one, and then we'll do one together. So keep that flow chart handy. So we have ascorbic acid, otherwise known as vitamin C, which is very important. Contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. What is the empirical formula of ascorbic acid? Okay, so what do we know? What are we given? Percents. So what can we assume? 100-gram sample. So these percentages simply change their label of grams. Okay? So once we determine the number of grams for each element, we then have to determine how many moles of each element are present. So we take their mass in grams, like for carbon, for instance, multiply it by its molar mass, or if you want to say divide it by its molar mass, whatever you want to say, making sure moles are on top. And you do this for each one. Okay? And you get the number of moles. What's the next step? After you determine how many moles, where do we go from here? The mole ratio. And how do we do that? By what? Why hydrogen? Got to go by the moles here. Which one do you want to use? Who has the smallest number of moles here? Oxygen. So we're going to take all of these numbers and divide it by oxygen. Carbon's really close. Okay? If by chance you happen to get into a situation to where you've got the calculated moles and they're identical, just pick one. Doesn't matter. Okay? So we're gonna divide all 3 of these moles by the number of moles of oxygen. And we get the following numbers. We get carbon with 1, because again, it's so close, you round it. Hydrogen with 1.33. Now I'm going to come back to that number. And oxygen with 1. Okay. Now, hydrogen. We get a decimal value of 0.33. According to our book, when you have a decimal value of 0.33, it is too far away from a whole number to round. So we can no longer attribute it to experimental error, that term I was talking to you about before. And you're probably thinking, and I hope you're thinking actually, well, when do we cut off, what decimal value do we actually cut off and say we can't round anymore? Well, my answer is there isn't an established number. Okay? There is not an established number. I have looked and looked and looked. There's nothing that I can find over the last few years that tells me at what decimal value do we say we can't do what we normally do. Okay? So what I've told past classes, for instance, if you had a decimal value of like 0.14, that's about where you want to cut off, okay? And really, that's just because we don't tend to see any more or that many decimal values above that, okay? So what we need to do in situations like this is we need to figure out how we can get that to a situation or a point that we can round it. And the best way to do that is to multiply by a whole number. Okay, so you can just go through the run here. So if you multiplied 1.33 by 2, what do you get? 2.66. Now, would you feel that that is close enough to round or no? Is it within that 0.14 range of a whole number? No. So 2 is not going to work. What about 3? What do you get when you multiply 1.33 by 3? 3.99. Do you feel better about rounding it then? Absolutely. But what you do to 1, you have to do to all. So you have to then take 3, multiply it by this 1 for carbon and this 1 for oxygen. And so you get the whole numbers of 3, 4, and 3. And that is what the formula for ascorbic, the empirical formula for ascorbic acid is, C3H4O3. Now, you're not going to see this situation happen very often, okay? But if you do, come back to this problem right here because you need to go and multiply it by a whole number to get it as close as you can so that you can round it. So let's do one together again. Practice exercise. We've got 5.325 gram sample of methyl benzoate, a compound used in the manufacturing of perfumes that contains 3.758 grams of carbon, 0.316 grams of hydrogen, and 1.25 grams of oxygen. What is the empirical formula? Well, we ask ourselves, what do we know? So where are we? What do we know in this question here? Are we starting with percentages? No. What are we starting with? Grams. So we don't have to do any quote-unquote conversions between percentage and grams. We just simply write the grams for each one. Okay? Just like this. All right. So now we are at the grams square, and we can only go one direction. And so our next step is to do what? Use the molar mass, okay? And so I'm just going to go ahead and front load the 1 mole on top for all 3, okay? What is the molar mass of carbon? 12. 12 grams. What is the molar mass of hydrogen? 1. And oxygen? Very good. And so I want you to calculate how many moles of carbon do we have? I'll wait for you to get your calculators out. You know it? You know calculate this? Okay, so let's try it out. Yeah. 3131? Okay. Very good. Okay, what about hydrogen? No. What's your calculator? For hydrogen? 0.316. And lastly, oxygen. 0.07. Is there any more after that? Well, that's good there. Okay. Excuse me. So now we're moving along. We are currently at the moles square on the flow chart. What's our next step? Mole ratio. And how do I find the mole ratio? Yes. And so, what is the smallest? Oxygen. Very good. So, I didn't write these far enough apart, so I'm just going to kind of just go over here. So, yes, oxygen is the smallest number of moles. So, here we have 0.3131 divided by 0.078. For hydrogen, we've got 0.316 divided by 0.078. Oh, I guess 81, sorry. And then basically oxygen is dividing it by itself. So if you want to, you can write this out. You don't have to, but there you go. Okay. So what would we get if we take carbon's moles and divide it by oxygen's moles? What whole number would you put down here? Exactly. 4. Is that what you all got? Okay. Now do the same thing for hydrogen. I bet you don't even need a calculator for this last one. What's it going to be? 1. Okay. So, again, what do these whole numbers that we just calculated, what do they represent? The subscripts. Now, you also might have a question of saying, well, how do you know what order the elements go for the formula? If you didn't, well, now you do. Okay. What I always recommend is put them in the same order in which you come across them in the problem. Okay. So we first came across carbon, then hydrogen, then oxygen. So we're going to go in that order when we're doing our formulas. Okay. So the formula for, what are we even, methyl benzoate, was that what it was? Yeah. Is going to be C4H4O. Excuse me. Questions? Just one more thing I want to go through. Okay. All right. Okay. Last thing I want to talk about is determining molecular formulas. Okay. Now, molecular formulas, again, are formulas that show you the exact number of atoms of each element in the formula. Okay. So there's going to be times where you're going to have to first determine the empirical formula and then determine the molecular formula. Then there's going to be times like this that they're basically going to give you the formula. They're going to give you the empirical formula, so you just have to do a really quick calculation to finish off the question here, like this. Mesitylene, which is a hydrocarbon found in crude oil, has an empirical formula of C3H4 and an experimentally determined molecular weight of 121 AMU. We are to figure out what the molecular formula is. So there's actually just not to use this word too many times, but there's a formula to solve for this, okay? In order to determine the molecular formula, we have to calculate what's called a whole number multiple. Basically, we have to determine the number in which we're going to multiply our subscripts by. So, I want you to highlight, star, whatever you need to, this formula right here. Okay? So in order to calculate the whole number multiple, we have to take the molecular weight, so the weight that we're typically given, so in this instance 121, and divide it by the empirical weight. Okay? And we've already calculated the empirical weights before. And that's where you take the formula, the empirical formula, for instance, C3H4, and multiply the subscripts by their respective masses found on the periodic table. So again, carbon is 12, hydrogen is 1. There are 3 carbons, so you take 3 times 12 and add to that 4 times 1 for hydrogen, and you get an empirical weight of 40 AMU. So you take that 121 AMU, which is the molecular weight of the substance they're using, divide it by the empirical formula weight, which we just calculated, and you get a number here. And much like what we just saw in the last example, there may be times where you get a decimal value. Go ahead and round that off. So what we're given here is a whole number multiple of 3. And so what we do is we take that whole number multiple of 3 and multiply that by all the subscripts involved. So 3 from the formula times 3, we get C9. 4 times 3, we get H12. So molecular formula is C9H12, and that's our answer. We could, if you were wanting to just double check if your formula was right, once you calculate the molecular formula, just find its molecular weight on yourself by doing what we just did right here. Okay? Taking 9 times 12 and 12 times 1. Add those together. You should get something close to 121. So let's do our own example here. Ethylene glycol. So this one's going to, oh man. This one's going to take a while. This is a situation where I said we're going to have to determine the empirical formula and then the molecular formula. What time is it? I don't want to rush through it. So what I'll do is I'll pause there. I'll start here in tomorrow's discussion. Okay? Have these flow charts handy when we're doing videos. I will also be sending out the next flow chart when we come to it next week. Okay? So you'll have that you can print off and look at. If you ever need any hard copies of something, let me know, and I can leave it down front at the table by the office, and then that way you don't have to worry about printing anything. Just give me a heads up, and then I'll have it down there ready for you, okay? So I guess I'll stop that.